Problem 1, Physics 2211, Test 3. So I'm going to refer to problem 1C. That's the main reason I'm doing this video. But to give you the prompt, the Singapore flyer has a radius r and rotates clockwise with a constant angular rate omega. Professor Juncker has a mass m and is riding in the gondola at an angle of theta from the positive y-axis. Part 1C is asking, what is the magnitude of the perpendicular component of the contact force exerted by the Ferris wheel on Professor Juncker? So if you just look right back at the diagram, I'll actually mimic it here on the paper. We have the Ferris wheel, and Dr. Juncker is at this part of the Ferris wheel. F parallels working in this direction, keeping Professor Juncker upright, and F perpendicular is working, inside the circle, into the circle like so, changing the direction as he goes around clockwise, in the clockwise direction. But 1C is asking, they're asking for the magnitude of the perpendicular component of the contact force exerted on the Ferris wheel. So the perpendicular component of the contact force. So if you look at where Professor Juncker is here, you can make sort of a triangle, and let's move that over here like so. You can outline the forces as they act on Professor Juncker as so. This is your F parallel, your F perpendicular, which is what we want, and then the force due to gravity. Here's your 90-degree angle, and this certain angle theta. So if we want to calculate that perpendicular force, we're going to need to analyze, of the contact force, we're going to have to analyze a few things. We're going to have to see the net forces acting on Professor Juncker. So we want to say that F net is equal to the contact force plus, or actually minus, mg, which is the force due to gravity. That's the FG you see here. So let me just write that. Right? So if we want to find the contact force, we're going to have to break this up into two pieces. Hold on. So actually, wait. Sorry. We're gonna have to analyze. Okay. So we want to find F contact in the perpendicular direction. And if we look at our triangle here, let's try to calculate that there. So we're going to say, according to this angle theta, F perpendicular, we're going to have to go and use cosine. So cosine theta, I first have to identify that cosine theta is equal to adjacent over hypotenuse, which is F perpendicular, divided by the hypotenuse, which is mg. So F perpendicular as a whole is equal to mg cosine theta. But that isn't everything, though, that we need. We have one component of the contact force, but that's the general contact. This is the general perpendicular force. But when it comes to contact force, you have to deal with the force due to gravity. Let me see if I can prove this even further by saying that F net in this case would be the force due to the contact minus, which is pointing in this direction, minus mg, the force due to gravity, which is pointing down. Right. Okay. Let's think about it like this then. The total forces acting in the perpendicular direction are equal to F contact in the perpendicular direction minus mg. Let's see. Alright, so let's subtract mg and see if that's the answer. I'm walking myself through it too.
What's the second word? What's the second most common word?
Oops, I apologize. There's a little more to this problem. So, let's say this again. The sum of the forces in the perpendicular direction is equal to the perpendicular force due to gravity plus or minus actually plus the force perpendicular due to contact, and that total amount is equal to mb squared over r. But in this case, because we're rotating, it's a normal vector there, normal unit vector. But since we're rotating, we have m omega squared over r omega r. I'll leave it like that. R. So that's the total amount. So if you want to just find the contact force, we're going to have to say that F contact in perpendicular direction is equal to that omega r squared over r subtracted from that mg cosine theta, which we got there. And that would simplify to m omega r minus mg cosine theta, which is our f contact in the perpendicular direction. And that is our final answer. And that's everything.